Pleasure to introduce Madhu Parthisarthi, who's visiting us from Illinois, University of Illinois, Urbana-Champaign. He's been doing research in logics and decision procedures for program verification, building verified systems. Of late, he's doing synthesis and using machine learning to infer invariants. And so today he's going to talk about natural proofs and quantifier instantiation.
Okay, so I'm going to talk about this work, which the results are fairly new. So the slides are raw, and the results also a bit raw in the sense that we probably haven't understood the consequences of our results completely to present it in a nice way. Okay, so with that caveat, this is joint work with Christoph Luding at RWTH and Lucas Pena, who is a student at University of Illinois. So I'm going to be sticking to this this verification context, this deductive verification. The problem is you have a program, let's say with assertions that you want to prove correct, and the method we're going to follow is annotated with strong enough inductive pre and post conditions and loop invariants. And then we generate verification conditions, which involve loop-free code. And this will be in the underlying logic, which can vary. And then we want to validate the verification conditions using a logic solver. Okay. So what logic do we use for these specifications, right? Actually, there's quite a lot of choices, right? The first kind of logics that come to mind are first-order logics, right? So, but as we will see, this is not quite enough. But traditionally, if you really want to automate everything, then you would like the verification conditions to be essentially in a decidable logic, right? And so, if it's quantifier-free or other logics that are decidable, then that will be fully automatable. And the idea is that these quantifier-free logics with some background theories, especially if they're quantifier-free, then they are combinable. If they meet some conditions, they're combinable using Nelson-Open, and that gives you a wide variety of theories that you could use and build decision procedures that are kind of independent of each other. Now, the attraction of decidable logics is that verification after annotation is fully automated, right? And that is actually quite useful because when you are actually verifying, right, you know that you'll either get back, well, time is one thing, but you'll get back either an error or it won't just keep on searching. If it keeps on searching, then I don't know whether it's actually maybe I wrote something wrong, right? And there's a little bit of uncertainty when you use the verification tool when you don't have decidable logics. But I think decidability can also be a trap, right? We need powerful enough logics, right, to do program verification, right? And I think at least the natural logics that we can use to express properties that we want to prove, right, will turn out to be undecidable, right? For instance, we do need quantifiers. We need logics, perhaps over certain theories that are undecidable, right? And typically, currently, I would say the reasons why we need more expressive power than decidable logics are to state properties about unbounded parts of your program configuration, like arrays and data structures and the dynamically changing heap, or to express, and even if you kind of go away from this by assuming certain libraries which manipulate state and keep these structures for you in some abstract way, you still need to argue about sequences, sets, functions, pure recursive functions of your data structure, and so on. And these are typically not going to be in decidable theories. Okay. So there is this obsession with decidability, and I've been part of that, right? We've been trying to work with decidable logics as much as possible. And decidability, as I said, when achievable is very good, right? You can actually it gives you predictability. It also gives you engineering of efficient tools because you can have competitions, and you don't have things which I think it's a little harder to have a competition if on some things you're going to fail, even proving, right? I think it kind of directs the engineering task better when you know it's a decidable problem.
So decidability doesn't mean efficiency, right?
No, it does not, right? It's more like a heuristic for building better tools, right? It kind of guides you, but and we have found that to be the case that, over time we've got better solvers with decidable logics. I think that's definitely a. We don't know how these mechanics work, but it seems to be true.
Can we say that the provers operate in a more predictable way on decidable fragments?
I think so. I think predictability.
Can we quantify that? Are there any
I don't know. I don't know if you can quantify that.
I mean, samples are definitely not predictable.
Well, it depends on what you call predictable. I think we have a lower bar for predictability than what stat solvers achieve now.
Let's just talk about variance in runs. So is the variance greater on a collection of points? If you keep doing runs with different random seeds on undecidable versus decidable problems?
So this agenda of building decidable theories, right? The ultimate question is, can we over time really obtain a powerful enough decidable logic using which we can prove all that we need to, right? And I think that question is not clear, right? I mean, everyone makes an epsilon step, does one more decidable logic, which is slightly more powerful. It's not clear where this whole thing is headed. So in my view, the answer seems to be no, right? I don't think we are heading towards the wonderful, decidable logics that will solve all the verification problems that we want.
I think your last slide, it's not just slightly more powerful, they're often incomparable, right?
They're incomparable as well. Well, typically you kind of branch out, maybe they're incomparable and then it'll kind of merge, and sometimes you do get reasonably robust things.
I'm not even sure what this means. You're saying you want a decidable logic for your verification conditions. But
Yes.
verification conditions, it depends on the proof you do.
Yes.
And so you're really saying you want to be able to get your proof by some manual steps down to the decidable fragment as easily as possible. In which case, you can never really say you solved the problem. You just say it's easier and easier.
Right. But so I'm being vague here, so I hope that's okay. I'm not making any concrete statements. I'm just trying to motivate natural proofs, right, which is a different way of looking at things. So the statements I make are going to be a little vague at this point. Okay, so we worked on decidable logics for heaps for a long time, right? And we had this logical strand. And there have been lots of logics for heaps, right? And there are logics also based on separation logics for heaps, right? Several decidable fragments have emerged, right? But I don't see this path towards a powerful enough logic, right? Which is also decidable, right? So two things which I notice is that as you get more and more expressive in your logic, right, the constraints that you need to put in your syntax become more and more awkward, right? You're not allowed. You're not just given a set of operators and say combine whatever you want. No. You should have some bizarre conditions that need to be satisfied. The second thing which I find is more troubling is that the decision procedures get more and more complex, right? By that I mean that even if you had something which you could solve earlier, right, and you threw it at the new decision procedure which handles a larger logic, right, it takes much longer to do that same problem, the same instance, right? So the general way of solving something, right, makes the procedures tend to work slower, right? They have to solve a larger class of problems more uniformly, and so you get they seem to, at least in our experience, strand. You start using all kinds of background things like monadic second order logic and stuff like that. And you start stitching these things up to get more expressiveness, and then they work really badly on even simple instances, right? And I think one should remember that decidability is a heuristic here. Automation is the goal, not decidability is not the goal, right? So here's the other way of looking at it, which I've been working on for several years, right? The idea in decidable logics is that you want to curtail your expressive power of your logic so that it becomes automatable, right? You automate reasoning, right? Now, natural proofs, the idea is different, is that you allow a logic to be quite powerful, right? You might restrict the style, but you don't typically restrict the expressive power, right? But instead of, and in order to automate, what you do is you look for a subclass of proofs, right? And these proofs are going to be, simpler to search for, right? And if you find a simple proof for your theorem, you're going to say, yes, I found it. And if you don't find a proof, then it's not going to work, right? So you're going to give up, right? So these are more like sound and complete ways, but incomplete ways, right, of solving problems, right? But we'd like to be build robust classes nevertheless, right? And possibly even a hierarchy of classes. So I look for the simplest proofs, and if I don't find it, I kind of enlarge the class of proofs I search for. Okay. So two things. The logic doesn't get awkward, right? You write what you want, right, given the style. And the proofs are not going to get complex because I'm going to kind of search for simple proofs only, right?
So when you say you have a growing class, does that mean the user's involved?
No.
With the proof? So you're not going interactive?
No. So typically, so you search for a simple proof. You don't find it, like quantifier instantiation is one, right? You could quantify more, right? You could instantiate more, right? That's a natural proof.
So when you say a simple proof, does it mean the simpler the proof is, the easier it is for the user to sort of have confidence in the proof? Or?
No, it's decision-wise, it's simple to search for a proof of that kind, right? The complexity of searching for a proof of that kind is.
But that would depend on the search strategy, right?
True, right? So, but it's going to be a subclass of proofs. I think that's the main thing, right? Okay, so we've been working on natural proofs for some time, and this is not practice as an industry practice, right? It's basically trying to make this work on a set of benchmarks. So what we have settled on is really first-order logic, right, with recursive definitions and background theories, right? And we have found that this is good enough to express properties about heaps. So we have a variant of a dialect of separation logic called Dryad that compiles into this logic, right? I don't know how to do automation on separation logic or other logics directly. I know only classical logics, so I'm going to stick to classical logics, right? So, but we do have more than first-order logic. We do have first-order logic with recursive definitions, right? And the heuristics that we use to prove a theorem are what we found in practice people do, right? If you give it manually to a person to prove it, right? What tactics would they use? And typically, what they use in the world of recursive definition is unfold these recursive definitions, right? Typically a few times, right? And then they do some kind of unification, right? At the level of term rewriting, you can think of it as unification. But it's basically, you can kind of mimic this as interpreting the recursive definitions that you have as uninterpreted functions, right? That kind of mimics the unification things that they do, right? So we looked at proofs of how people normally prove things, right? And the simple proofs were really based on this, right? This was enough to prove most of the things. And so the resulting formulas, so what we do is basically unfold the recursive definitions. If I have the recursive definition of a list, I would just unfold it a few times, right? And then I would basically interpret the recursive definitions as uninterpreted functions, right? And I'm in a refutation-based context, so I'm looking at a formula and trying to prove it's valid by showing its negation is unsatisfiable, right? So if doing this already gives me an unsatisfiable formula, I'm done, because I've shown that the theorem is valid, right? So I don't need to actually unfold. This introduces an abstraction, but this abstraction is fine, right, and kind of mimics what people do. Moreover, the resulting formulas are actually in decidable theories, right? So you can unfold and then send it off to an SMT solver. By the way, this is not at all, that only we do. Everyone essentially does this, right? Natural proofs is more like a name for, talking about this in some way. But Daphne does it, right? If you have recursive definitions in Daphne, which are pure functions, Daphne unfolds these functions and gives it to the SMT solver, right? Everyone does it.
So the simplicity is measured by the number of times you have to unfold the recursive definition. Is that the definition?
I think the simplicity is got to do with, you could think about it that way, but it's basically the fact that you're abstracting from what you want to prove, right? And thereby you're looking for a simpler proof that thing holds, right? So if you don't succeed in this, doesn't mean that it doesn't hold. You don't get concrete counterexamples or anything like that, right? Maybe the theorem is false, or maybe you need to do more, right?
So one way maybe to think about this is if you're proving something for an object in the heap, how much of the rest of the heap do you really care about, right?
Right. So if it's the variant of Dryad actually has it. It forces you to write recursive definitions so that you don't rely on something very far away, right? So typically, recursive data structures, you can have the quantification restrict in a guarded fashion so that it refers only to something that you already have in your hand, right? And so Dryad actually does all that. So make sure that you don't do arbitrary quantification so that they are more amenable to recursive proofs, right? Inductive proofs. So here's an example. So I have the definition of a list here, right? Either it's nil and the heaplet of this list is empty. I don't really need this, right? Or the x is not nil and the next element to x is a list, and x does not belong to the heaplet contained in this list, in the next of the list. So this is the way you would do in separation logic, right? I'm just writing it using first order logic. And H list is defined using, again, recursion. It's either the empty set if x is nil, or it's x union this. Now, this turns out to properly define lists, right? If H list, however, makes sense only if x points to a list, otherwise you shouldn't use it. It may be spurious, right? But the intended semantics is a least fixed point semantics, right? So we need first order logic with least fixed points to express these kind of properties, right? And we are using background theories here. It's sets, right? I'm using union and so on, right? But once I unfold things, then this will actually be in a decidable theory because this kind of theory of sets is decidable. So the question we wanted to ask was, why do these natural proofs work so well, right, when they do, right? And why do they fail so miserably on simple properties? So they don't actually work well all the time, okay? There are very simple properties on which they don't work well. Is there any completeness theorem we can prove about the simple heuristic that we have, right? That is, if we unfolded the definitions larger and larger, can we prove every theorem, for example? Okay. So what we have now is a set of theorems where we can answer such questions. All right. So this has got to do with quantifier instantiation, right? Now it turns out that unfolding recursive definitions is really very similar to quantifier instantiation done, which is formula-driven quantifier instantiation. For instance, if I have this definition of lists, right? So unfolding this for one more time, which is next of x, right? I want to write the definition for next of x. Then it's the same as replacing x with next of x in this definition, right? So unfolding is really like taking this universally quantified variable x and instantiating with something else, which is another term, which could be n of x. Now, formula-driven quantifier instantiation is a common strategy for handling universal quantification. It's incomplete, but e-matching has existed for a long time. And roughly, I'm going to follow this instantiation strategy that I'm going to take any terms that I get in my formula, and I'm going to instantiate the universal variables using that. Okay? And that's similar to unfolding as well. So here are the main contributions of this work, right? We explore various logics, like pure first-order logic with background theories, and first-order logic with recursive definitions, and show the completeness of formula-driven term instantiation for some of these fragments of these logic. And in particular, for first-order logic with background theories, right, we have a fragment called the safe fragment that admits completeness, right? And we can show that the verification that we are doing kind of falls in that class modulo recursive definitions, right? Once you get rid of recursive definitions, and I'll tell you how, right? It kind of falls in this class, and this roughly explains why natural proofs are actually so powerful, because they're actually complete in that sense. The second thing we have is that we will not have completeness results for first-order logic with recursive definitions. It's clear that you cannot build a complete procedure for first-order logic with recursive definitions, right? And so we mitigate this using certain techniques, right, which are related to invariant synthesis as well, right? And so it seems to be a new kind of way. But a lot of people have been doing this in the theorem proving community already. I think what we're doing is we're doing it in the first-order context, right, so that we reduce this to first-order reasoning for which we can prove completeness. Okay. So first, a reminder of classical results. And I'm sorry if you know this very well. It's just that I've been with audiences where they may not remember it. So first of all, first-order logic admits sound and complete reasoning. This is Gödel's completeness theorem, right? First-order logic is undecidable, right? And validity of first-order logic is RE because it admits a sound that has a complete proof system. You know that you can enumerate proofs and prove any theorem in first-order logic, right? So validity is in RE, and satisfiability is not in RE because it's not decidable, all right? And it also turns out that recursive definitions and least fixed point cannot be expressed in first-order logic, right? And there is no complete procedure for first-order logic with least fixed point. If you throw in that, you can do non-halting or something and then show that you cannot have an RE procedure for it. And so first-order logic with least fixed point, in a full generality, there cannot be a complete procedure for it, right? You can't hope to prove every theorem. But for first-order logic, right, building complete decision procedures is theoretically possible, right? You can just enumerate proofs. And if you have your axioms, and axioms are enumerable, right, which they are typically even for the background theories, right, you can just keep on enumerating proofs, and they will find it at some point. But it's not useful in practice. You're not going to do this. So we are not interested in any enumeration which will be complete. It's clearly true. What we want to show is quantifier instantiation, which is particularly useful seems to be particularly useful, right? Whether that is complete. Okay. Now, though I just now said it should be possible, there's actually a fundamental problem of doing this with verification logics, right? And so consider a logic for verification conditions that is powerful enough that it's undecidable. Okay. Now, unlike first-order models, the models I would deal with in verification are finite and enumerable, right? The program configuration is not an infinite object. It is a finite object, right? It can have integers, it can have unbounded integers, but still it's finite, right? And any set of finite structures you can enumerate. So I can enumerate all models, which means satisfiability of the problem, of the logic, is in RE, right? So validity cannot be in RE, okay? So the fact that these models are finite means validity becomes harder, right? And I kind of lose the lovely thing I had in first order logic, that validity is actually, you had a complete procedure for validity, for first order logic. I cannot actually take it down to program verification. So,
Finding is very useful.
what's that?
Bug finding is very useful.
Bug finding is easy, yes.
Is useful.
So yes, so this is why you can test, but you can't verify, right?
So what about sequences? Are those admit finite models or?
So it all depends on your axiomatization. So I'm looking at only first order logic. So if you wanted for sequences, you have to axiomatize it in first order in first order logic. Could be in an infinite axiomatization, but it should be in a recursively enumerable one, right? So piano arithmetic, Pressburger arithmetic, for example, is a infinite axiomatization of.
So the model of a sequence, is that a finite model or is that a?
Yeah, I mean, in program verification, it's finite, right? I'm just saying that infinite things are actually easier than finite things for proving validity, right? But we don't have infinite things here. So there is inherently a problem in building complete engines for verification. We will come back to this. Sorry?
What do you consider fractals finite? Say fractals with a finite area but infinite.
We don't do that in verification, but I don't know about fractals and their theory. Yeah. So here's the simplest setting, which is first order logic. No recursive definitions and no background theories. This is pure first order logic. Is quantifier instantiation complete? And it turns out that it is. So first consider pure first order logic, and we are going to do refutation based, so we'll negate it and show unsatisfiability. First we scolamize and we remove every all existential quantification by replacing it with functions, right? And then we do systematic formula driven term instantiation, right? So create an iteratively growing conjunct of quantifier-free formulas where in every time you replace any universal quantified variable with any of the terms that occur in your formula so far. Okay. So more precisely, let's say we want to show we have some kind of finite axiomatization A1 through AN, and let's say it's universally quantified, and I want to show phi or not phi is implied by it, right? So I negate it, and I have this formula to show it's unsatisfiable, right? Then what I do is I start with phi, the thing which I want to prove under the axiomatization, right? And at every time I take the universally quantified formulas and I instantiate it using a term in my what I had before, right? In Xn, right? So at every time I get quantifier-free formulas, right? And X star is the union. If I go on forever, X star is the union of all of them. Okay, and indeed it's true that this is a complete procedure. If I generate Xn iteratively and I check, right, whether it's satisfiable. If it is unsatisfiable, there will be some point at which I halt and find it to be unsatisfiable. This is a combination of Herbrand's theorem. So Herbrand's theorem really says that you can always build a universe with only your terms. Once you scolamize, you can only build it with your terms, right? And you need to, what we had to do is slightly modify it because this is really driven by the formulas that you have. The instantiation is driven by the formulas. So you have to kind of prove it again. And then compactness, so with Herbrand's theorem, you really get X star, that the set of all things will be unsat. And then by compactness theorem for first order logic, right, we actually get that at some point Xn, it must hold. Okay? So quantifier instantiation works really well for first order logic. Okay, now let's move to many sorted first order logic, right? So this is a setting which we had to define because it's kind of best fit our yeah.
So there's something called local theories, right? Local theory extension. Is this related to that or?
I think so, but I'm not sure. Maybe we can take it offline.
Mm-hmm.
Yeah. So here I have a foreground universe, right? So I have many sorts, right? I have a foreground universe which is uninterpreted, and I have a background theories that are interpreted. So this could be arithmetic, sets, whatever you will, right? So I have a set of background theories, but it's very important that these sorts are completely disjoint, right? And what I have is a universally quantified formula, right, over this vocabulary, right? And I have uninterpreted functions that kind of map across these vocabularies. Okay? And the rough idea is that I'm going to model my heap here, right? These locations are modeled here, and maybe a function from here to integers will tell me what data is stored there, right? A function from a pair of locations could tell me the heaplet that is characterized by that list segment or some data structure, and so on. So roughly, this is going to be my the logic that this kind of uninterpreted world, the program configuration that I'm looking at. But the contents of the program configuration in terms of primitive data types are going to be kind of captured using the background theories. Now, so this is the world we want to belong to, right? And then I want to take this formula, which is only universally quantified. The outermost quantification is only of the foreground universe, because I will want to talk about my program configuration using universal quantification. And internally, I could have more quantification, which is in the respective theories, right? Let me just allow that. But the outer quantification is in the foreground. And now I could ask the same question, right? I could fix some theories, and I could say I could do quantifier instantiation, right? And when I do quantifier instantiation, these variables will be replaced, but I'm not going to touch alpha, right? So I'm just going to do quantifier instantiation in my foreground universe, right? And I ask whether that term instantiation is actually complete, right? Now the background theories, if I had the axioms for them, I could do instantiation using those axioms as well, and then everything will be complete. But I don't want to do this. I really want to use black box solvers here. So I don't want to start instantiating here, right? Arithmetic should be solved by an arithmetic solver. And it turns out that this is not true, right? There are simple examples that demonstrate this, but quantifier instantiation, just doing blindly on the foreground, is not going to be complete. And the reason is that the background theory can actually restrict the foreground theory in ways that will preclude you from finding a proof if you just looked at the terms that you get by instantiating in the foreground. So the main technical result we have is that quantifier instantiation is complete in the setting for what are called safe formulas, a safe fragment. And this is very easy to understand what the safe fragment is. So a term is called foreground guarded. T naught is the foreground universe. So a term is called foreground guarded if it contains variables only of the foreground sort. And the formula is safe if every subterm that you have is guarded, right? Which basically means that you cannot derive a term in the foreground universe, right, using functions over universally quantified variables in the background universe. You can't say there's a list associated with, or a location associated with an integer. You can go the other way around, right? But you can't come back to the foreground universe. So,
how does it relate to this essentially uninterpreted fragment?
Right. So essentially uninterpreted fragment doesn't have background theories typically, but it is true we can prove the.
It does allow background theories. Yeah.
Yeah. So if you have two sorts, it will allow. Yeah. Right. Yeah. So we can prove as a corollary the EUF thing as well. Right. So the Bernays-Schoenfinkel class as well.
Mm-hmm. So this generalizes the
yes.
EUF.
Yes. So there are two simple restrictions that you could follow to meet this fragment's conditions. One is not to have functions that go from the background sort to the foreground sort. If you don't have any functions, there's no way you can construct anything wrong, right? If you had only forward functions, then it's fine. The other way is to have no explicit universal quantification on the background sort. If you say I won't quantify over integers explicitly, then also you're fine, because then you're not going to generate this. And in practice, what we have found is that the VCs that we generate on heaps actually meet both the conditions. You need to meet only one, but it meets actually both the conditions, right? You don't need to quantify over integers, right? You quantify over elements of a list, and then you can look at the keys associated with that, but you're still using a forward function, and you're not quantifying over integers.
So if you want to say that two lists have the same length,
Same what?
if you want to say two lists have the same length,
Yeah. So you'll have a length function, which is recursively defined. Now, we can't define length with first-order logic yet, but then you would say that the length of these two functions are the same. That's fine. Length is a function which goes from nodes to integers. And that's fine.
It's not uncommon to quantify over the elements of an array at particular positions, right?
Right. So arrays will be done differently. You will have a foreground universe of array names, let's say A or whatever. Then you'll have a function that maps A and an index to some value. And that's okay. So you can have your domain can be a cross product of any of the universes, right? That's fine. But your range has to be always a background one. So an array can be defined this way as well.
I typically want to go from array and index
Yes.
to, say,
A value.
location or value or something,
Right.
right?
So that's fine.
That's fine because the location is not necessarily background, right?
Oh, if you have a pointer as in a true pointer, as a, like an integer thing, that's harder. I'm talking about here pointer locations being abstract locations.
so if you have A sub B sub J, like if you're using an array to index another array,
Yeah, you can do that too, but yes. So
you can?
yeah, but you don't have to. You don't write it the same way. But you can do it.
Well, there you're using the array content as a pointer into another array.
You don't write it that way. You can model it differently so that.
So you still
Yes.
can this?
Okay. So I don't want to go into the proof of the main theorem, right? I'm going to look at some ramifications, right? One is that if you do not have any quantification over the background theory, then term instantiation gives you only quantifier-free formulas, right? And over the background theory, if they are nice and they have they're Nelson-Open combinable, then you can actually have a decision procedure. And this decision procedure, not a decision procedure, a complete procedure, right? The complete procedure will just do this, repeat till it's unsatisfiable, do one more level of term instantiation, and check whether that set of instantiation holds or not, right? And this actually gives you a complete procedure for the safe fragment. Okay. Now, the first thing which we had when we had this result is that this must be wrong, all right? Because surely if I have a background theory of natural numbers, I can define lists, finite lists, and therefore least fixed points easily using arithmetic as a background theory, right? So I can say a nil is a list, its length is 0, and then a non-nil element is a list if the next of x is a list, and that is one, length of x is now one more than the other one, right? You can define, what you're doing is you're using recursion, but now you're piggybacking your recursion on the background theory, which supports recursion, right? But then this actually goes wrong, right? Because lists with numbers is incomplete, right? You cannot build a complete procedure for it, right? So it'll contradict a completeness result if you can actually do this, okay? So what is going on? It turns out that the whole thing has got to do with non-standard models, all right? It turns out that Pressburg arithmetic, though it's a complete axiomatization, right, admits non-standard models. And you're reasoning only with respect to a background theory and not a background model, right? You don't have a true model, you're only a background theory. So I could have, this kind of a list, right, where I can claim x reaches nil, but it doesn't reach at any finite time, right? And to justify it, I could have the length function map x to a non-standard element. So non-standard elements, non-standard arithmetic is where you have your normal natural numbers, and let's say you can have a copy of z after that. Okay? And it turns out that using first-order logic, you cannot distinguish between that and just natural numbers, right? But using that non-standard model, I can actually create one which doesn't have finite length. And so your encoding into Turing machines to show incompleteness all will break down. So it's actually, in fact, complete. Right? The completeness result does hold. And it doesn't contradict our theorem. So now we also get a kind of understanding of natural proofs. Right? Formulas given in first-order logic with least fixed point. Right? Let's say this is the definition. Right? Now, what you notice is that if I gave you something with the least fixed point definition and you just did unfolding on it, then really you do not distinguish, you're not capturing the least fixed point semantics at all, right, when you unfold. If all that you're going to do with your recursive definition is to unfold it, then what you're really treating it as is an if and only if operator, right? The fact that it's a least fixed point is kind of lost, because you never said anywhere that you're going to use it that way. Okay? So you can look at natural proofs as actually doing two things. One is replace least fixed point definitions with an if and only if. Right? Now this has semantic loss, right? You're not expressing least fixed point. Right? And phase two is doing quantifier instantiation, which is essentially doing a recursion definition unfolding. And what we now know is that this is actually, I'm going to argue now that phase two is actually complete. Okay? And remember, for completeness, we need safety, right? So I'm going to argue that what we're actually generating is safe. So it turns out that when you model heaps, right, you have locations, nodes in the foreground universe. You have pointers modeled as uninterpreted functions in the foreground universe. You have data stored in data structures. Those go from foreground to background, like a key stored in a data structure. Right, recursive functions and all are from, like sets of keys in a data structure in a binary search tree would be from foreground to background. Heaplets are foreground to background. And recursive definitions like BST are predicates which are defined using these other functions, but they're still predicates on the foreground which are uninterpreted.
My question still applies, sorry. If I have an array with indices are integers to their background, right? So then I have a function from the background theory to the contents of the array, which is foreground.
So it's array cross integers to integers?
No, array cross integers to something in the foreground, like values.
To values. So we're not doing locations as true locations that you can do pointer arithmetic on. They're abstract locations?
I mean, let's say I have I have an array of tuples.
Right.
Okay, so I have a function from array cross integer to pairs, to values.
Pairs.
Something in the foreground, right?
Yeah. Right.
So that doesn't seem to respect this.
Okay, so maybe I've not thought about that. Maybe it's true. It's possible. So in the natural proof work, we don't do that. We don't have arrays. We deal with purely recursive data types.
Okay.
Right? And that's the context which I'm saying that this is true. So arrays, we do consider in the paper, but that's only for the decidable fragments. We also get decidability results on the way. So there might be things which we cannot model yet. Right.
So if you have lists of lists, can you model that?
Yeah.
Okay.
But the pointers have, again, you're not doing arithmetic on it, but you're just doing. So these are actually safe, right? Because you have only one-way functions, and you don't need quantification on integers typically, right? So it's actually safe by the other condition as well. And so we actually have this term instantiating that we do for natural proofs in that work is actually complete, right? Because it belongs to the safe fragment, provided you have replaced least fixed point with fixed point definitions. So this phase is actually complete, right? And there is a semantic gap introduced in phase 1. So why can't we prove things, right? So in natural proofs, there are lots of simple things we cannot prove. And the user has to give axioms for it. But in our work, usually it turns out that if you define two data structures, the relation between them is typically not provable, and you actually give that, like lseg xy, and you have a disjoint list y, then you get a list x. If you unfold, you'll never be able to prove this theorem, right? And it turns out that the reason is the phase 1, the semantic difference is the 1, and again, non-standard models is the reason why you get into this problem, right? The reason why it can't prove it is because it's not actually true in the if and only if semantics of list segments and lists, right? There's a semantic gap between least fixed points and fixed point semantics, right? So there's actually, if you had x, even though it never reaches y, right? This is the next relation, right? Never reaches y. I can declare x to y to be a least segment as long as I declare all of these to be list segments, right? I can still do that, and there's a model for it. So we couldn't prove it because it wasn't valid in the first order world. So non-standard models crop up all the time in this work. We found problems in the literature, in PhD theses, and so on. So there was not, there were theorems which are now actually, again, open because of this. I won't comment on this.
I see. So all this stuff around shape analysis and logics with the reachability predicate is assuming a least fixed point semantics, right? And so you are abstracting somehow over that. So what is your abstraction?
It's a fixed point and not a least fixed point. So when you're doing unfolding, you're saying if and only if.
All these logics of certain restricted forms of heap for which you can have completeness, right? So I'm trying to, so he has abstractions for that, or he has classes of logics. So I just wonder what is the relation here between all the stuff Mooley and Roman and Gang have done, where they basically don't have any background theories, but they have just very hard problems because of reachability in the heap.
Right.
No, but those fall into your other class of the increasingly idiosyncratic logic fragments. Right?
I see, okay.
I think there ought to be a name for this phenomenon. That the harder you push on the decidability boundary, the more idiosyncratic your logics and models become.
Yeah.
Okay, so I think I'm running out of time. So is that correct?
Yeah. 10 minutes.
Okay. So I want to tell you a little bit with fixed points, because what we have essentially done is remove least fixed points and said everything works well. But what with least fixed points? And the idea is that how are we going to prove these things after all if we are not going to do this unfold and match, right? So this brings to this other part, which is, so remember that first order logic with least fixed point cannot have a complete procedure, right? So anything that you introduce is going to look like a heuristic, right? And what we do is we introduce induction principles, right, that bridge this gap between least fixed point and fixed point, okay? And we do this kind of uniformly, systematically, guided by the formula that we want to prove, okay? And obviously this has got to do with invariant generation as well, because a program is just, you can look at it as first order logic with least fixed points, the entire program, right? And so you're proving now that whole program is correct without loop invariance now, right? So you're actually generating loop invariance by doing these induction principles. So, the crucial thing is that we have to stay within the first order logic framework, right? Induction principles are typically second order, right? But you want to kind of stay in the first order logic framework. And in some sense, we're instantiating the formulas that we want to declare our inductive systematically. So we have some in the paper, right? So I'll just give you one, right? One is this: for every x, if I have to show that r of x implies psi of x, where r has some definition phi r. There's a recursive definition which is using least fixed point, okay? And then what I do is introduce this induction principle, which basically says that the partial fixed point of this operator, right, if psi, right, if what I want to prove, right, is a prefix point of the definition of R, then R implies phi. Okay? This is essentially saying that whatever I want to prove, I'm going to prove that inductively based on the definition of R, right? I'm going to show, and formally this becomes a prefix point, right? So if I can show that psi is a prefix point of rho is the definition of R, right? Then R implies psi. I mean, that is true, right? And this brings in the least fixed point semantics into picture, right? But the induction principle is completely first order. There's no mention of least fixed point. There are slightly more general versions than this paper, but the most important thing is to see that it's guided by the formula that you want to prove. You write it as this form, that this recursively defined object implies something else, and then you generate this automatically. And then introducing this induction principle in turn leads to other induction principles to be added. So you will add one induction principle like this one, and then this might have something else, and that will introduce, if you regroup it, right, you can see it of this form, and you can instantiate one more of another kind, right? You can kind of keep going. And actually some examples actually require that you do that. And then what we showed is that all the things that we could not prove in natural proofs, right? All the things where the user needed lemmas, right? Before the user needed to give lemmas to help it to prove, were all proved using a couple of these induction principles. Okay? So these are there were not too many axioms, right? There were about 150 programs, but these have got to do only with the data structures and not with the programs, right? and there are simple things like if the binary search tree, then it's a binary tree, right? You can't prove that using unfolding, right?
So Joxan Jafar has a couple of papers on this.
Yes, so that is correct. So that's in the CLP framework, and right. So there's a little
separation logic, right?
Right. So the key thing here is that to do it in the first order logic framework, right? So that once you do this, you know you can build a complete procedure after that, right? We also tried it on some programs which are not to do with heaps, like.
But he addresses the same kind of examples,
Yes,
right?
exactly. I mean, the same thing we did, he addresses the same thing. So we proved some things like McCarthy 91, for example. It proved it in 2 iterations. It was able to find the right loop invariant, right, and actually prove it correct. So this is what emerges, right? If you want to do natural proofs, then one thing is to take first order logic with least fixed point, which I think is a good logic to work with, right? Replace least fixed point definitions with fixed point definitions, right? But use induction principles to bridge this gap. Otherwise, you're not going to get the power you need. And the second phase is, unfold and do quantifier instantiation, and this part is in fact complete, right? You must ensure safety along the way. So I don't know whether the array of pointers will work, right? But this is only if you can ensure safety is the completeness result true. Okay? And if you further ensure that the resulting formulas when you instantiate terms are quantifier-free, then you have the ability to use SMT solvers with various theories, and you will combine because they're quantifier-free, and by Nelson Open they'll combine. So you have something which should work fast, right? It's worked fast in the settings we have tried, but in general it should work fast. Okay, so that's it. So conclusions: a new theorem that proves completeness of term instantiation for multi-sorted, uninterpreted combination of theories for the safe fragment, and then the systematic introduction of first-order induction principles that seem to work in some settings at least. And I think with these two, right, we have an understanding and a robust reformulation of this completely ad hoc strategy that we were doing, which is take everything express in first order logic least fixed point, just unfold. It seems to work, right? And it seemed to work was gotten from proofs where people were writing, and we thought, they're such simple proofs. Why don't we use them, right? But now I think we have a more robust understanding of what exactly is happening. Okay, and there is a paper by Gay and Demura, and this is actually very similar. We found it after we did this paper, but it's very similar and very different at the same time. So the basic difference is that it's not a multi-sorted universe, right? And then the logics for which you can prove such a theorem become very restricted, right? You can't even take two universally quantified variables and check equality between them, right? Because equality is an uninterpreted symbol, right? And they won't allow that, right? And in fact, you can't really. The proofs are all different. Even the first theorem that I said for first-order logic being complete without any background theories, even that doesn't go through if in that setting. So, and of course, there's a huge amount of work in finding induction principles in the theorem proving community. ACL2 did a lot of work, right? We're probably mimicking such strategies in the first-order logic world, right? And what we do have is this completeness thing and reduction to SMT and using SMT solvers. So future work, I would like to build SMT-like solvers, meaning efficient solvers for first-order logic with least fixed points, right? I think there'll be a lot of applications because first-order logic with least fixed point is incredibly powerful, right? The second thing is we don't know these induction principles for how will they work for programs that do not involve heaps. We don't know. It's probably easy to try it on and see how it works. But we were a little surprised that McCarthy did not take like 100 iterations, right? It just took 2 iterations and out-popped the invariant. And that was a little surprising. So we should investigate that. And of course, how does it compare, right? Because all these are going to be incomplete techniques, right? How do they compare with other techniques such as interpolation? Would be good to know. The third thing is I think first-order logic with least fixed point and background theories may be the right logic to do for host-style reasoning or deductive verification, right? We certainly need this much power, right? We need data structures. And also, in general, we need this kind of power to have expressiveness of the weakest pre. There's a paper by Blas and Gurovic, actually, that a long time back, that argues that we actually should do this because you don't need arithmetic. You don't have to show something complete by mapping everything to arithmetic with addition and multiplication, for which you don't have any solvers anyway, right? That's how most completeness proofs go, right? But actually, with first-order logic and least fixed point, you can get that power to express the weakest pre of any program, including loops, right? And that maybe is useful, right? And we do have now some ways of handling first-order logic with least fixed point automatically. The third thing is we probably don't need much more. I'm not sure about that. I'm a little hesitant to go beyond first-order logic because I just don't know how to deal with automation beyond first-order logic, right? I don't have compactness. I don't have completeness. I don't know term instantiation. I know nothing to work with. So it's going to be very hard to go beyond first-order logic, at least for me, right? So maybe this is a good logic to work with. Thank you.
So, right, so you started out talking about the importance of decidability, and then most of what you said was actually about completeness. And so what about decidability? In other words, if I have completeness, I don't necessarily get countermodels. Right? And if I'm actually doing a proof, countermodels interactively, countermodels are very important. We use them for refining inductive hypotheses, and we use them when things are going wrong, and we have to understand why. So, under what circumstances can I get countermodels?
I think countermodels you can do by symbolic test input generation, right? You could bound your heap, you could bound things, and then get countermodels.
What if
It's just that I don't know whether
there's no finite countermodel to mine?
it would be a finite. I mean, your program configurations are intended to be finite. So there should be a finite counter model.
Well, yeah, maybe, but once I sort of abstract it into the logic, now I can.
No, without abstraction. I'm just saying when you just prove a VC, you could try it for.
Standard models, as you said.
I hope you don't want non-standard models as your count example, right? So I'm just saying that
What I'm saying
just
is
normal
you can-
symbolic execution should do counter models.
These are counter models to the invariants.
Yeah, but that's right. I don't want a counter model to my program. I want a counter model to my VC.
Yes.
See what I'm saying? It's not the same thing.
Yeah, counter model to your VC. You could do.
Because I've done abstraction. When I've got to my point of having my VC, I've done abstraction. For example, I got rid of these fixed point semantics or whatever. So if I send my VC into my theorem prover, right, and it should either eventually come back with a proof, or it should eventually come back with a counter model. In which case
I just
you have
think that
decidability.
these two procedures might be totally different. If you want to prove something versus find count examples, these may be different things, right?
But I'm not- what I'm
Because
saying is-
we cannot possibly target finding complex count examples and finding simple proofs at the same time, right? So
But I think you're missing my point about the usefulness of counter models.
no, I'm not saying that. I'm just saying that you can do counter models by some other technique.
Well, what if if you could do that, then your logic would be decidable, right? Because if I can get counter models, right? If counter models are RE and if proofs are RE,
Proofs are not RE. They're going to have least fixed point. They're not going to be RE.
right? But let's say I've thrown away the least fixed point semantics, right?
Then it is complete. It is decidable. Yes, I agree. In fact, I've argued that all your VCs. I mean, the program configurations are enumerable. Its satisfiability is an RE. So if you've done away with this,
We have to talk about this offline. 'Cause we have
Okay.
fundamental misunderstanding here.
Let's thank